This lesson is about random variables. The definition of a random variable is fairly straightforward, but it may not be how you would first think of the definition if you were trying to define it yourself. So the definition of a random variable is it's a function which goes from the sample space omega to the real numbers. Let's look at an example. So suppose we flip a fair coin 3 times, and the outcome of the flips are heads or tails. The sample space then is you could get 3 heads, 2 heads and a tail. You could flip heads, then tails, then heads. You could flip heads, tails, tails, and so on. So you can see all of the sample points here, which are the outcomes of 3 flips in order. And to make this a probability space, the probability of each outcome would be 1 out of 8, because there are 8 possible outcomes, and the coin is assumed to be fair. So we're going to define the random variable x by saying let x be the number of heads flipped. So x maps each one of the sample points to some point in R, to some real number, right? So for example, x of tails, tails, heads equals 1 because there's only 1 heads that's been flipped. And x of heads, heads, heads equals 3 because there are 3 heads that have been flipped. So it takes each outcome. You can think of, remember, we're running some experiment, and there's these outcomes to the experiment. And x takes that outcome and maps it to a number. So when flipping a coin, you're going to get outcomes like heads and tails, and so you get like heads, tails, heads, for example. But of course, we might want to measure the number of heads, so we would map that heads, tails, heads to 2. And that's where the random variable comes in. So a random variable just maps sample points to numbers. A little bit of notation that you probably won't have to use a whole lot in a first probability course or when you're studying for the actuary exam. But given a subset A of R, we can define the subset of omega as the points of omega such that omega is an A. So this is like everything that x would map to A. And we usually write that as the inverse of x on A, or what they usually call a pullback function. So x to the minus 1 of A is a pullback. If A is a 1-point set, then instead of writing it this way, we could also just write x equals A, the set of omega such that x of omega equals A. And we even reduce that down to the simpler notation, just x equals A. So just below, I'm going to show an example of what this means, but we're going to use this notation a lot for random variables, and this is what this notation is really saying. So whenever we're saying the random variable x equals A, we mean the set of all points omega such that x of omega equals A. Similarly, if we're on a half open interval from A to B, then to say the set of omega such that x of omega is in that interval, we just write A is less than x is less than or equal to B. So let's look at what this means for some sets in the coin flip example. Let's let A be the set 0, 1, and we could write this out in formal notation with using set theory as the set of omega in the sample space such that x of omega is in 0, 1, which would be tails, 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 heads, tails, 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 heads, tails, and tails, tails, heads. So if any of these 4 outcomes occur, there are 0 or 1 heads. And that would be the set of points in omega in which x is in the set A. So we could write this as x inverse of A. That's the same set. We could also write this as x is in A. Or we could say 0 is less than or equal to x is less than or equal to 1. Or equivalently, since x is going to be 0, 1, 2, or 3, in this case we could say like x less than 2. So all of these would be notation for that same set. And probably most commonly you're going to see it as notation 3 or notation 4. So just some algebraic operation on the random variable. So another quick example, the set x equals 2 is the set of points in omega in which there are exactly 2 heads. So that all of these points, heads, heads, tails, tails, heads, or tails, heads, heads, would have exactly 2 heads in omega, and those are the points exactly on which x equals 2. So x equals 2 is represented by, well, it is that set. It's a representation of that set. So something a little bit more advanced, we could talk about measurable sets. So not all sets are necessarily measurable. Remember that it's not possible to measure the probability of every set. So we could look at only sets A such that x and A is measurable. But this is a little bit more advanced topic, and so we're going to take for granted that we're always looking at measurable sets. And we can also compute the probability of such events. So say we wanted to know the probability that 0 is less than or equal to x is less than or equal to 1. Well, we just saw that that is the event of these 4 points. Tails, 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 heads, tails, 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 heads, tails, or tails, tails, heads. One of those must occur. And each one of these has probability 1/8. So since there's 4 points, there's 4/8 chance that this happens, or 1/2. So there's a 1/2 chance that 0 is less than or equal to x is less than or equal to 1. And that's how random variables work. You can compute the probability by pulling it back to the state space and just doing regular probability with a state space as we've done before, although we won't usually think of it that way. In fact, the state space and the probability measure on the state space usually will be sort of hidden from us in a lot of problems on random variables, and we'll just care about the probabilities of the random variables themselves. We could also compute the probability that x equals 2. So the probability x equals 2, going back to the state space, is the probability of the event heads, heads, tails, heads, tails, heads, or tails, heads, heads, where we have exactly 2 heads, and that's 3 points. So the probability is 3/8, and therefore the probability that x equals 2 is 3/8.